ultra-high bandwidth, specifically targeting that interconnect bottleneck for things like GPUs.
HBM sounds like a direct attack on the pathway problem.
It is. Another technique is zero-copy transfers. This avoids physically copying data between, say, the CPU's memory and the GPU's memory. Instead, they can be given shared access to the same physical memory region, eliminating redundant data movement.
So the design of the interconnect, whether it's a traditional bus or a more complex network on chip, SoC, is just as critical as the memory components.
Just as critical. A poorly designed interconnect can starve even the fastest processors and memories.
Okay, this next one is becoming increasingly important and, frankly, a bit scary. Security vulnerabilities, specifically things like side-channel attacks. Memory systems can be leaky.
This is a huge area of concern and active research now, yes. Side-channel attacks don't break encryption or exploit software bugs directly. Instead, they exploit physical information leaked by the hardware during its normal operation.
Physical leakage, like...
It could be tiny variations in power consumption when the chip performs different operations, or subtle differences in the timing of operations, or even electromagnetic radiation. Attackers try to measure these physical side channels and correlate them with the secret data being processed.
And memory is vulnerable to this.
Very much so. For example, researchers have shown that analyzing the minuscule power fluctuations when writing different data values, a 0 versus a 1, to SRAM cells in a cache can potentially reveal sensitive information. There are also attacks based on timing. Observing cache hit miss patterns can leak information about memory access sequences, which might reveal parts of an encryption key or other secrets. This is especially concerning in shared environments like the cloud.
So someone running a program on the same physical server could potentially spy on another user's data just by watching cache behavior.
That's the risk, yes. Techniques like flush plus reload or prime plus probe exploit the shared nature of caches. Even things like subtle physical degradation effects in memory cells, like negative bias temperature instability, have been explored as potential side channels.
Wow. And you mentioned that some optimizations, like HLS techniques, could even make this worse.
Potentially, yes. Certain ways of partitioning memory or scheduling operations in high-level synthesis, if done without considering security, might inadvertently create or amplify these side-channel leakages, like creating predictable power signatures.
That's deeply concerning. How are designers fighting back against these subtle attacks?
It requires a multi-pronged approach. Memory encryption is one technique, encrypting data before it's stored in memory, though this adds overhead in terms of performance, power, and area.
Okay.
There's also research into designing secure hardware components from the ground up, for example, creating SRAM cell designs that leak less information through power consumption, or adding hardware mechanisms to randomize timing or inject noise to mask the real signals.
So building countermeasures right into the silicon.
Ideally, yes, but the most fundamental shift is towards security-aware design methodologies, including in HLS. This means security can't be an afterthought bolted on at the end. It needs to be considered alongside power, performance, and area right from the beginning of the design process. A secure-by-design philosophy.
So PPA is becoming PPAS. Power, performance, area, and security.
You could definitely say that. Security is now a first-class design constraint for memory hierarchies in modern SoCs.
Okay, we've talked about the layers, principles, and constraints. How do designers actually optimize all this? What are the key techniques they use, maybe leveraging tools like HLS?
Right. Let's look at optimization techniques. Architecturally, we've touched on pipelining and multi-channel architectures. Pipelining overlaps operations for throughput. Multi-channel boosts raw bandwidth. Both aim to keep data flowing.
And buffering.
Buffering techniques are crucial too. Using small, fast, temporary storage buffers like FIFOs or small SRAMs can smooth out data flow between different parts of the system, decouple producers and consumers of data, and reduce the number of slow, expensive accesses to main memory.
Beyond the big architectural stuff, what about organizing the data itself? You mentioned locality.
Yes, techniques that enhance locality are key, and this often bridges hardware and software. Memory partitioning is a big one, especially with HLS.
Partitioning. Breaking things up.
Exactly. Taking a large array in memory and physically splitting it into multiple smaller independent memory banks on the chip. Why? So you can access different parts of the original array simultaneously, in parallel. This dramatically increases the effective bandwidth to that data structure.
And HLS tools help automate this.
Yes, HLS tools provide directives like pragmas in C++ code,
Right.
e.g. hashtag pragma HLS array partition, that tell the tool how to partition the memory, completely splitting it cyclically, etc. This gives the designer high-level control over the physical memory layout.
What else in that vein? Data flow.
Data flow optimization is another powerful HLS technique. It focuses on optimizing the movement of data between different processing functions or loops. The goal is to keep data flowing directly from one unit to the next, often through dedicated FIFOs, minimizing the need to write intermediate results back to main memory and then read them again.
Of creating dedicated data pipelines between processing stages.
Precisely. It encourages a streaming style of computation, which can be incredibly efficient for throughput. Techniques like data reuse are part of this, trying to keep frequently needed data in local registers or caches for as long as possible.
You mentioned FIFOs there. How else are they used?
FIFOs, first in first outs, are workhorses in HLS design. They act as elastic buffers, great for connecting modules that produce and consume data at slightly different or variable rates. They provide high throughput, point-to-point communication, often bypassing slower general-purpose memory interfaces entirely.
So they help decouple parts of the design.
Exactly. And then there's using efficient data types. We touched on this with area optimization. Choosing the smallest possible data representation that meets the application's precision requirements, like using 16-bit fixed point instead of 32-bit floating point, if you can significantly reduces memory size, bandwidth needs, and power consumption. HLS tools often provide libraries for these custom precision types.
So all these techniques are really about the designer, often using HLS, carefully orchestrating how data is stored and moved to match the computation.
That's a perfect summary. It's about co-optimizing the algorithm, the data structures, and the underlying hardware implementation, using HLS as the enabling tool.
Let's talk more about high-level synthesis, HLS itself then. It seems absolutely central to modern SoC design, especially for memory optimization.
Yeah.
You said it translates C++ or System C into hardware descriptions.
That's the core idea, yes. HLS tools take code written in high-level languages, which describe the behavior or algorithm you want, and automatically generate the detailed register transfer level RTL code, like Verilog or VHDL, that describes the actual digital circuits needed to implement that behavior.
What are the big advantages of using HLS for memory design?
Several huge ones. First, productivity. Writing C++ is vastly faster and easier for most engineers than writing complex RTL code manually. This dramatically cuts down design time.
Okay, faster design cycle.
Second, and maybe even more importantly, faster design space exploration. Because it's quicker to modify the high-level code and add HLS directives, pragmas, designers can rapidly experiment with many different architectural trade-offs.
Like trying different levels of pipelining or different memory partitioning schemes.
Exactly. They can explore variations for power, performance, and area much more quickly than if they had to rewrite RTL each time. This ability to iterate rapidly is crucial for finding optimal memory hierarchy configurations, given how many parameters are involved.
So HLS makes designing complex systems possible in reasonable timeframes.
It certainly facilitates it. Systems being designed today, especially in areas like AI acceleration, would be incredibly difficult, if not impossible, to design purely at the RTL level within market timelines. HLS raises the abstraction level.
But you hinted earlier it's not magic. Does
What?
using HLS mean you don't need hardware expertise anymore?
That's the crucial nuance. Well, HLS makes the process of generating hardware more accessible, achieving truly optimal results, getting the best possible power, performance, and area, PPA, or quality of results, QRR, still requires significant hardware design knowledge.
Why is that?
Because the designer still needs to understand how the HLS tool is likely to interpret their high-level code and directives, and how that translates into actual hardware structures, timing, and resource usage. You need to guide the tool effectively. HLS is a powerful assistant, but it needs expert direction to produce the best outcomes.
So it's not just a compiler for hardware, it's more like a guided synthesis process.
That's a good way to put it. It empowers designers to work at a higher level, but deep hardware understanding remains essential for high-quality results, especially for something as critical and complex as the memory hierarchy.
You mentioned HLS uses directives or pragmas to guide the synthesis.
Hmm.
Can you give examples of key ones impacting memory?
Sure. We already mentioned hashtag pragma HLS array partition for splitting arrays into parallel banks. That's fundamental for memory bandwidth.
Okay.
Then there's hashtag pragma HLS pipeline. This tells the tool to pipeline a loop or function, overlapping operations from different iterations to improve throughput, which often involves optimizing memory access patterns within the loop.
Increases parallelism within a task.
Right. Hashtag pragma HLS unroll is another loop optimization.
Ugh.
It replicates the loop body multiple times in hardware, allowing iterations to run truly in parallel, which can dramatically reduce latency but uses more chip area, often requires parallel memory access to feed the unrolled instances.
More speed, more area.
The classic trade-off. Hashtag pragma HLS data flow enables that task-level pipelining we discussed, optimizing data movement between functions, often using FIFOs implicitly.
Keeping data flowing between blocks.
Yes. There are also directives for resource sharing, hashtag pragma HLS resource, where you can tell the tool to share specific hardware units, like multipliers, across different operations to save area, potentially at the cost of some performance if sharing creates contention.
Controlling area usage.
And importantly, there are directives for interface optimization. These specify how the synthesized block should communicate with the outside world, particularly external memory like DDR RAM. Directives like MAXI configure efficient AXI master interfaces for burst transfers, while Axis configures AXI stream interfaces for high-throughput streaming data, often used with FIFOs.
So these pragmas are how the designer gives detailed instructions to the HLS tool about the desired hardware structure.
Exactly. They are the primary mechanism for controlling the microarchitecture generated from the high-level code, and using them effectively requires understanding their hardware implications.
Which brings us back to needing hardware expertise, even when writing C++.
Precisely. An average software programmer without hardware knowledge might struggle to use these directives to achieve optimal PPA. HLS bridges the gap, but doesn't eliminate it entirely.
Are there specific HLS tools that are prominent in the industry for this kind of work?
Yes, several major players. Xilinx Vitis HLS, now part of AMD, is widely used, especially for targeting Xilinx FPGAs. It has strong support for memory hierarchy design, AXI interfaces, and good co-simulation features for verification.
Okay, Xilinx AMD. Intel must have one too.
Correct. The Intel HLS compiler, formerly Altera, targets Intel FPGAs. It also offers robust features for controlling interfaces, parallelism, memory structures, accelerated verification, and things like variable precision data types, which are useful for AI.
And the big electronic design automation EDA companies. Cadence, Mentor.
Yes. Cadence Stratus HLS is a popular choice, particularly strong for ASIC design, custom chips. It supports C, C++ DOS, System C, and has features like physically aware synthesis that considers layout effects early, plus good low-power optimization. Mentor Catapult HLS, now Siemens EDA, is another major player, also supporting C++ System C, focusing on productivity, verification, and offering advanced features for power optimization and design exploration, including AI-driven flows.
Any open source options?
There are some academic and open source HLS tools as well, like LegUp and Bamboo, though the commercial tools generally offer more mature features, support, and integration for complex SoC design.
So a range of powerful tools, but the choice often depends on whether you're targeting an FPGA or an ASIC and which vendor's ecosystem you're in.
That's often the case, yes. Each tool has its strengths and target applications.
Okay, even with these amazing tools and techniques, designing memory hierarchies isn't easy. What are the really big, persistent challenges that designers still grapple with? You mentioned the memory wall at the start.
Yes, let's revisit that. The memory wall problem is still arguably the #1 challenge. It's this fundamental gap between how fast processors can compute and how fast they can get data from memory.
It's not going away.
It persists because processor speeds, driven by Moore's law and architectural tricks, have historically improved much faster than memory latency and bandwidth. This means the processor spends an ever-increasing fraction of its time just stalled, waiting for data. It's a massive performance limiter, especially for data-hungry workloads like AI, machine learning, and scientific computing. HPC.
And it wastes energy too, right? Moving data costs more than computing on it.
Significantly more energy, often orders of magnitude more. Moving data from DRAM to the CPU can consume far more power than the actual arithmetic operation performed on that data. This is forcing a rethink, pushing computation closer to the data, sometimes called processing in memory or near-memory processing.
So what are the cutting-edge approaches trying to break through this wall now?
Things like Compute Express Link, CXL memory, are a big deal. CXL allows CPUs, GPUs, and accelerators to access shared pools of memory with high bandwidth and low latency, potentially across different physical boxes, creating more flexible and scalable memory systems.
Expanding the memory pool coherently.
Right. Multi-channel architectures, HBM, unified memory like Apple's M series, these are all direct attacks on the memory wall. But its persistence really highlights that we need continuous innovation in both hardware architecture and software optimization, particularly improving data locality to minimize data movement in the first place.
Another challenge you mentioned is actually getting the best results out of HLS, achieving optimal quality of results, QRR. It sounds like hitting the PPA jackpot is hard.
It's incredibly challenging. One major reason is the sheer size of the design space. HLS tools can generate a vast number of possible microarchitectures from the same high-level code, depending on how directives are applied.
An exponential number of choices.
Potentially, yes. Exploring this huge space manually to find the absolute best configuration for power, performance, and area is practically impossible for a human designer. It's too vast.
And checking each option takes time.
Checking each candidate design is slow. Running HLS synthesis might take minutes to hours, and then you need to run logic synthesis, place and route for physical design estimation. It adds up, so you can only explore a tiny fraction of the possibilities. It's like searching for a needle in an infinite haystack with very slow tweezers.
And this ties back to needing expertise.
Yeah.
Because you need intuition to guide the search.
Exactly. That hardware expertise is needed to prune the search space intelligently, to know which directives are likely to yield good results for a given algorithm and target technology. This expertise gap limits how widely HLS can be adopted by people without a deep hardware background, despite its potential.
Are there efforts to use AI or machine learning to help with this QRR problem?
Yes, that's a very active area of research. Using ML to predict the PPA outcome of certain HLS directives or configurations before running the slow synthesis process could massively speed up design space exploration. But this requires good training data, which is still somewhat limited, especially diverse open source data sets.
Okay, a final huge challenge: debugging and verification complexities. Ensuring the hardware generated by HLS actually works correctly and matches the original software intent. That sounds nightmarish.
It's definitely one of the most time-consuming parts of the HLS flow. Subtle bugs can creep in during the translation from high-level CC++ to low-level RTL.
What kinds of bugs?
You might get behavioral mismatches if the designer makes incorrect assumptions about hardware timing or parallelism. There can be issues with latency and sensitivity bugs that only appear under specific dynamic runtime conditions related to data arrival times, making them very hard to find in standard simulation. Sometimes, optimizations performed by source-to-source compilers before HLS can even introduce subtle bugs that are incredibly difficult to trace back.
So how do designers gain confidence that the synthesized hardware is correct?
CRTL co-simulation is a cornerstone. Here, you run the original CC++ code and the generated RTL code side by side using the exact same test inputs, test bench. You then compare the outputs cycle by cycle or transaction by transaction to ensure they match perfectly.
Simulating both worlds together.
Right. It catches functional mismatches. But simulation can't cover all possible corner cases, especially for complex timing-dependent bugs. That's where formal verification is increasingly important.
Formal verification. Using math proofs.
Essentially, yes. Formal methods use mathematical techniques to rigorously prove certain properties about the design or to prove functional equivalence between the C code and the RTL. It can find obscure bugs that might be missed by trillions of cycles of simulation. As designs get more complex, formal verification is becoming indispensable for achieving high confidence.
So verification is a major bottleneck and requires advanced techniques.
Absolutely. Robust verification strategies are critical for successful HLS adoption.
Let's shift to some exciting developments. What are some cutting-edge memory technologies and real-world examples really pushing the envelope? You mentioned high bandwidth memory, HBM. Tell us more.
HBM is a true architectural shift. Instead of placing DRAM chips beside the processor on a circuit board, HBM stacks multiple DRAM dies vertically, one on top of the other.
Stacking them up.
Yeah, and connecting them using tiny vertical wires called through-silicon vias, TSVs, that pass directly through the silicon layers. This stack is then placed very close to the main processor or GPU die on a common base layer called an interposer.
What's the benefit of all that complexity?
Massive bandwidth and lower energy per bit transferred. By drastically shortening the physical distance data has to travel and providing a very wide interface, like 24 bits or more, HBM achieves bandwidth far exceeding traditional DDR memory, and less distance means less energy wasted driving long wires.
So it's perfect for AI and GPUs that need to process tons of data.
Exactly its target market. The demand for HBM, especially for AI accelerators, is exploding. You see market forecasts with compound annual growth rates over 50%, maybe even 60-70% in the coming years. It's essential for feeding the beast of modern AI models.
Well, it's probably expensive.
It is. The stacking and packaging technology is complex and costly. But for high-end AI and HPC applications, the performance efficiency gains justify the cost. Its growth is a direct indicator of how badly we need to overcome that memory wall.
What about other novel memory types? You mentioned magnet-resistive RAM, MRAM, earlier. Sounds exotic.
MRAM is really interesting. It's a type of non-volatile memory, meaning it holds data even when the power is off, like flash memory. But unlike flash, it uses magnetic properties, electron spin, rather than electrical charge, to store data.
Magnetic storage on a chip.
Yep. Specifically, spin transfer torque MRAM, STT-MRAM, is becoming prominent. The key advantages are non-volatility combined with fast read and write speeds, much faster writes than flash, very high endurance, it doesn't wear out quickly like flash, and radiation tolerance. Plus, it has low latency, approaching SRAM speeds in some cases.
So wait, non-volatile like flash, but fast like SRAM. Could it replace both?
That's the potential holy grail. It could potentially unify storage and working memory in some applications, simplifying the hierarchy. It's being seriously looked at for embedded systems, replacing embedded flash, maybe replacing some SRAM and caches, especially where low power and non-volatility is key, in areas like automotive, industrial, IoT, edge devices.
So we might see chips with MRAM integrated alongside DRAM and SRAM.
Very likely. It adds another option to that heterogeneous mix, offering designers a new set of trade-offs, especially blurring the lines between traditionally volatile cache RAM and non-volatile storage.
As chips get more cores, you mentioned managing access to shared memory becomes tough. Tell us more about non-uniform memory access, UMA architectures.
Right. In a traditional symmetric multiprocessing SMP system, all processors have equal access time to all parts of main memory. This is called Uniform Memory Access, UMA. But as you add many cores, they all contend for the same memory bus, creating a bottleneck.
The shared highway gets jammed.
Exactly. Now, SMA addresses this by partitioning the main memory and associating chunks of it directly with specific processors or groups of processors, nodes. A processor can access its local memory much faster than it can access memory attached to a different processor, remote memory, hence non-uniform access times.
So it gives each processor its own faster lane to some memory?
Kind of. It improves scalability by reducing contention on a single global bus. If a task and its data can be kept mostly within one UMA node, it runs much faster.
But doesn't this make programming harder? You need to know where your data is.
It absolutely does. To get the best performance from UMA, software needs to be UMA aware. The operating system plays a big role here, trying to allocate memory for a process on its local node and scheduling threads to run on the node where their data resides, processor affinity. But programmers might also need to explicitly manage data placement for optimal performance.
And cache coherence gets more complex across nodes.
Yes, maintaining coherence between caches and different NUMA nodes typically requires more sophisticated directory-based protocols, adding overhead. But for large multi-core systems, NUMA or NUMA-like designs are often necessary to scale memory bandwidth effectively.
Let's ground this in reality. Can you give some real-world examples? Apple's M-series SoCs have made waves. How do they handle memory?
Apple's M-series chips are a fantastic example of innovation here. Their key feature is the Unified Memory Architecture, UMA.
Unified memory.
Yeah. Unlike traditional systems where the CPU and the integrated GPU have separate, dedicated pools of memory, system RAM and VRAM, and have to constantly copy data between them.
Which is slow and power-hungry.
Exactly. Apple's UMA puts a single large pool of high bandwidth memory that is directly accessible by both the CPU cores and the GPU cores, as well as other accelerators like the neural engine.
So no more copying data back and forth.
Largely eliminated. The CPU and GPU can work on the same data structures in the same memory pool with very low latency access. This dramatically boosts performance, especially for graphics and AI tasks that share a lot of data, and it's more power efficient.
And they use fast memory for this pool.
Yes. They typically use high-bandwidth LPDDR memory. The M4 chip, for instance, boasts 120 GB of memory bandwidth. Combine this unified memory with their sophisticated caches, L and L2 for performance and efficiency cores, and you have a very potent memory subsystem that directly tackles the memory wall by minimizing data movement.
Okay, what about the king of high bandwidth memory, NVIDIA GPU architectures? How are they structured?
NVIDIA GPUs are masterpieces of memory hierarchy design tailored for extreme parallel processing. At the lowest level, each processing core within a streaming multiprocessor SM has its own set of registers. Then, within each SM, there's typically a fast L1 cache and a region of software-managed scratchpad memory called shared memory. Shared memory allows threads running within the same SM to cooperate and share data with very low latency.
So fast, local communication within a processing block.
Critical for parallel algorithms. Then there's a larger L2 cache that's shared across multiple SMs, acting as an intermediate buffer. And finally, the main off-chip memory, which is the large pool of graphics DRAM, GDDR, or increasingly for high-end AI GPUs, HBM.
HBM again, for that massive bandwidth needed by thousands of cores.
Absolutely. NVIDIA's architecture is relentlessly optimized to maximize memory bandwidth utilization and height latency. They use wide memory interfaces, sophisticated caching, prefetching techniques, and compression to feed those thousands of parallel cores. Minimizing data stalls is life or death for GPU performance.
And finally, how is HLS being specifically applied for AI and machine learning accelerators? Seems like a natural fit.
It's a perfect fit. AML algorithms often involve complex custom computations like matrix multiplies, convolutions that are highly parallelizable but might not map perfectly onto standard CPU or GPU architectures.
So custom hardware is better.
Custom hardware accelerators, often implemented on FPGAs or as ASICs, can provide significant performance and power efficiency advantages for specific AI workloads. HLS is crucial here because it allows domain experts, like ML researchers, who might be more comfortable writing algorithms in C++ or Python, to more easily translate those algorithms into optimized hardware accelerators.
So it lowers the barrier to creating custom AI chips.
Significantly. Instead of needing a team of RTL experts spending months manually designing the hardware, HLS enables much faster iteration and development of these custom accelerators. Designers can quickly explore different parallelization strategies, data flow optimizations, and memory architectures using HLS directives.
And HLS helps with optimizing data types for AI too, like reduced precision.
Yes, that's another key area. AI models can often tolerate lower numerical precision using 16-bit floats, 8-bit integers, sometimes even 4-bit integers instead of standard 32-bit floats. This process is called quantization. HLS tools make it easier to implement these custom precision data paths and memory structures, which drastically reduces the accelerator's area, power consumption, and memory bandwidth requirements, often with little impact on the AI model's accuracy.
So HLS is really enabling this explosion in custom AI hardware.
It's a major enabler, yes. It bridges the gap between high-level algorithm description and efficient hardware implementation, making bespoke AI accelerators much more feasible to develop.
So let's sort of wrap this up. Looking back at everything we've discussed, it's just abundantly clear, isn't it? Memory hierarchy design isn't just some detail. It's a critical, maybe the critical aspect of SoC development.
Absolutely. It fundamentally shapes the power, the performance, the physical size, the PPA of any modern chip. And that memory wall we started with, it's still the ghost in the machine, the primary driver pushing innovation. Plus, now we have security as a non-negotiable fourth dimension.
Right, PPAS. And high-level synthesis, HLS, has really emerged as a key tool in tackling this complexity.
Definitely pivotal. It boosts productivity, allows for that crucial rapid design space exploration using those optimization directives we talked about.
But it's not magic. We kept coming back to the fact that getting the absolute best quality of results, that optimal PPA, still really hinges on having deep hardware expertise.
And the verification challenge, making sure the complex hardware HLS generates actually works, is driving adoption of advanced methods like CRTL co-simulation and increasingly formal verification.
So looking ahead, what's next? Where is this heading?
Well, expect memory hierarchies to get even more complex, even more specialized, driven by that relentless memory wall and the absolutely insatiable data appetites of AI, ML, HPC, and now edge computing too.
We'll see more mixing and matching of memory types.
For sure. Even more heterogeneous integration. You'll have HBM for the crazy bandwidth needs, maybe MRAM popping up for its non-volatility and speed, perhaps EDRAM for density, all coexisting with traditional SRAM caches and DRAM main memory.
And all connected intelligently.
Connected within unified memory spaces or sophisticated NUA-like fabrics, all designed to minimize those costly, energy-hungry data transfers. Keep the compute close to the data.
What about the design process itself? AI helping design AI chips.
Exactly. AI-driven design is a huge emerging trend. Expect HLS tools and other EDA tools to increasingly use machine learning for automating design space exploration, predicting PPA, suggesting optimal pragmas, maybe even generating parts of the architecture. This could make optimizing these complex memory systems much more efficient and maybe more accessible.
Having an AI co-designer?
Yeah.
And security.
Security by design will become standard practice. Those side channel vulnerabilities we discussed mean security has to be baked in from the start. We'll see more inherently secure memory components, secure protocols, and design flows that evaluate security alongside PPA throughout the process.
No more bolting it on at the end.
No way. And finally, I think we'll see the lines blurring even more between hardware and software optimization.
Yeah.
Software will become even more responsible for managing locality, maybe through more explicit programming models or smarter runtime systems that dynamically adapt data placement and computation scheduling to the underlying hardware. It's a true co-design future.
So wrapping it all up for our listeners, what does this all mean for you?
Well, it means the devices you use every single day are undergoing constant fundamental reinvention at the memory level. These complex challenges are driving the innovation that makes your next phone faster, your AI smarter, your cloud services more responsive.
And mastering these complexities, understanding the trade-offs, leveraging advanced tools like HLS, anticipating these future trends in heterogeneous memory, AI-driven design, and security. This is absolutely paramount for anyone involved in developing the next generation of chips.
Chips that are high performance, energy efficient, and secure, the foundation of our digital world.
It leaves you wondering, though, as we solve one bottleneck like the memory wall with things like HBM and unified memory, what new bottlenecks will emerge next? What's the next wall we're going to hit? Something to think about